Mass balance problems, blended component. Two distillation columns operate in series and serve to separate a mixture of cyclohexane and toluene. In the first column, 1000 kg per hour of the mixture 60% cyclohexane by weight is in the feed. Out of the top of the first column, the product is 83% cyclohexane, flowing at the rate of 650 kg per hour. This flow of 650 kg per hour is then fed into the second distillation column, which produces a top product that is 95% in cyclohexane, flowing at the rate of 480 kg per hour. Determine the flow and percent by mass of cyclohexane in the bottom stream from the both distillation columns. This example shows an application of the mass balance when we have more than one unit operations. We have two distillation columns. We have column 1 and column 2. We know that 1000 kg per hour of the mixture 60% cyclohexane and 40% of the toluene is fed into the column 1. This column separates two products, M2 650 kg per hour coming out of the top of the distillation column, and the bottom's product M3 with the composition X3 and 1 minus X3, where X3 is the fraction of cyclohexane in the bottoms of the first column, and 1 minus X3, that's the fraction of toluene in the bottoms of the column 1. The distillate from column 1 is fed into the second distillation column, which produces the top output with mass flow rate of 480 kg per hour and the composition of 95% of the cyclohexane and 5% of the toluene. Output from the second distillation column, bottoms, has mass flow rate of M5 and the mass fraction of cyclohexane in the M5 stream is equal X5 and toluene fraction 1 minus X5. In order to decide which unit operations we will start working with, we have to perform the analysis of number of degrees of freedom. Looking at the general process flow diagram, having the first column, that's our first unit, and having the second column, second unit, we have to draw a total overall system that includes column 1 and column 2. And then we have to go and perform the analysis of number of degrees of freedom by analyzing the number of unknowns, number of independent equations. So for unit 1, we have two unknowns. We have M3 and X3 with the two unknowns, and number of independent equations is 2. For the second column, we have two unknowns, M5 and X5. We have two independent equations. Why? Because we have two components, cyclohexane and toluene. So N, which is equal to number of unknowns minus number of independent equations, 2 minus 2 is equal 0 for column 1, and 2 minus 2 is equal also 0 for column 2. When we run the analysis of N for the overall system, we will find out that we have four unknowns, M3 and X3 and M5, X5. It gives us four unknowns with the two independent equations having toluene and cyclohexane two components. 4 minus 2 would give us 2. So looking at the N numbers, we can start solving the problem from column 1 or column 2. We cannot start solving the equations based on the overall mass balance since N is equal to 2. So let's go back for a moment into the process flow diagram and look at the known and unknown variables in our problem. M1 is input into the process is given. The M3 and X3, that's our unknowns here. for the column 2, M5, X5 are unknowns, and M4 is known. It is equal to 480 kilograms per hour. Our strategy here, because n is equal to 0, our strategy here is start from unit 1, from distillation column 1, since n is equal to 0, and here we can calculate M3 and X3. Then we go to unit 2 to calculate M5 and X5. Balances that we can have for our process here for column 1 include the total balance, because this is the process where we don't have the chemical reaction. Input is equal output. That's our general mass balance equation. For column 1, the total mass balance would be equal to 1000 kilograms per hour. Input into column 1 is equal our output, which is 650 kilograms per hour coming out of the top of the column, plus M3. One equation with one unknown, and when we solve it, our mass flow rate of distillate coming out of the first distillation column is equal to 350 kilograms per hour. Then, in order to calculate the composition of the distillate coming out of the first column, we have to perform cyclohexane or toluene mass balance. So in this case, I'm showing here the cyclohexane component mass balance, where the input into the process is equal to 0.6, that's the 60% of the feed, times 1000 kilograms per hour, is equal output 650 times 83%, that's the top output, plus X3 times 350, that's the M3 that was calculated from the total balance. After substituting the numbers, the X3 is equal to 0.173, which is 17.3% of the mixture. That's the composition of cyclohexane, kilograms of cyclohexane per kilogram. To calculate M5 and X5, we have to go to column number 2 and perform the total mass balance on column 2. Input is 650 is equal output 480 plus M5, one equation with one unknown, and M5 is equal to 170 kilograms per hour. And component mass balance, in this case I'm showing cyclohexane balance on column 2, which is equal to the input, and this input is the output from the first column, from the top stream coming out of the column 1, 83% times 650 kilograms per hour is equal to 95% times 480, that's the output of the distillate from the second column, plus X5 times M5, and as you can notice here, M5 was calculated from the total mass balance on column 2. One equation with one unknown, and X5 is equal to 49%, which means that we have 49% of cyclohexane per kilogram of the product coming out of the bottoms line from the second distillation column. To summarize our calculations, we have M3 350 kilograms per hour with the mass fraction of cyclohexane 17.3%. M5 is 170 kilograms per hour with the mass fraction of cyclohexane that is equal to 49%. Corresponding benzene fractions from the first column is equal to 0.827, 82.7% of the benzene per kilogram coming out of the bottoms from the first column, and the fraction of the benzene coming from the second distillation column is equal to 1 minus X5 is equal to 0.51, 51%.